Hello and welcome everybody to a new video. So it's been a little while since my last video. I've been incredibly busy with something I alluded to in my last video. It's a new project to be coming up, probably the biggest project I've ever done up to now. Can't talk about it just yet. There's still some stuff to finalize, so that will be coming soon. And yeah, I'll share it all with you guys. It's very exciting. But while that's been on the go, I've also been working on another small project, which has kind of been kicking my ass a little bit. I was hoping to have a much more full-featured video about it by now, but it's just taken a really long time to do it. So I'm kind of at a logical point now where I want to kind of just pause, share progress I've made so far on it with you guys, and yeah, just talk about it a little bit. So project that I'm doing is going to involve basically an embedded system thing, which is my custom STM32 microcontroller, but I'm also going to need to log data, and what I'm logging data to is a little SD card. So I have this set up on the board, this turned out to be the easy part, making the chip talk to the SD card. The STM32 I'm using has SDIO hardware built into it, so it's actually pretty straightforward to get it just to communicate with the chip. But the unfortunate thing is the libraries that I'm using, or the basic HAL library that I'm using, all it does is it just communicates with the chip. That's it, doesn't do anything else. So the chip, basically, it just sees it as a big pile of bytes, and you can read those bytes in blocks, and you can write those bytes in blocks, and that's it. So there's no formatting or anything as such, or it doesn't know anything about formatting. So that's the part that I have to do, is I have to write some code that can handle writing and reading to the SD card in a sensible format. And the reason I want to do that is because I want to be able to write files, log files, data files to the SD card. Then I want to be able to plug them into my computer, and I want my computer to be able to understand them. I could obviously just start writing binary data to the SD card in no particular format, but then I'd have to use custom software on my computer to be able to read that data and make sense of it, which I'd rather not do. So what I thought the easy thing to do would be just to write like a FAT32 file parser and, implement that for the SD card. I will say that does exist. There is Rust crates that exist that are no STD crates that I could just pull down and would do that for me. But me, being me, I want to do it myself and at least learn how it works. So that's what I'm doing. That is the part that is kicking my ass. This is the part that I didn't realize quite how difficult it was going to be. So it's taking ages to do it. But I'm learning while I'm doing it, and I'm kind of having a lot of fun doing it. There's a lot of, sort of algorithmic programming stuff, which is the stuff that I really, really love doing. So yeah, I'm having fun learning it and doing it. And yeah, so purpose of this video, I want to just explain what I've learned so far about how FAT32 file systems work. You may be wondering why I'm using a FAT32 file system. Few reasons. It's generally pretty common for the likes of SD cards and removable media to use the FAT32 format. Obviously, you could format them to whatever you want, but FAT32 is pretty common. It's also fairly straightforward. So in terms of me writing a parser or that implements FAT32 file system support, it's relatively straightforward to do it compared to other ones. Doesn't mean it's not kicking my ass, but it's relatively straightforward. So that's why. So yeah, that's about it. That's the setup. Let's jump into a little bit about how does a FAT32 file system even work, and what code have I written up to now. I will say this isn't going to be a Rust video just yet. I will probably have a later video, make this a series. I think it'll end up being where I talk about the implementation in Rust of this. But for some quick and dirty prototyping, I've written it in Python. So we have my code open here. Link in the description for this code as well. It's all still work in progress, but I'll share it with you guys anyway. Basically, yeah, I'm writing it in Python as a prototype, and then I will, once I have it working, I'm gonna translate it into Rust, and then publish it as a no STD crate probably, so that I can reuse it myself. Well, I may not publish it onto cargo or whatever, but yeah, I'll basically make it a module that I can include into my project so that I can read and write to an SD card, basically. So yeah, this is not going to spend too much time looking at this. You can read this yourself. This is just some basic setup instructions. I'm using Python 3.13, and I use UV to do dependency management and stuff. So PyProject all set up in here. Again, not terribly complicated. Have a read of this if you want to run this yourself. Only thing to note, if you're running it yourself, you'll need to alter the main.py file in here to set a different disk name to be whatever drive you want to have this connected to. For me, it's dev disk 4 happens to be the SD card that I have plugged in, but yeah, that could be anything. So yeah, just really need to check that. So let's talk about. So yeah, I guess I don't know exactly where to start with this one. But let's just maybe talk about some random stuff to do with disks and drives and what all that even means on your computer. So I'm going to talk all this. Basically, I'm on a Mac, so I'm going to talk mostly about Mac stuff, star Linux environment. So most of what I say here will also be applicable to a Linux environment. If you're on Windows, things are a bit different, but concepts still apply mostly. So if you're on a star Linux system, you'll have at the top level directory, you'll have the /dev directory. So what's in this is basically connected devices that are connected to your computer. So if you do ls, which will just list all the files, you get all these files, and there's tons of stuff in here. So there's like TTY ports, which are like COM ports basically, and then you'll also find you have all the disks are in here. So you'll see you have a disk 0, and then you have disk 0, S1, S2, S3, which those are the partitions basically on the disk. So for us, we're interested in disk 4, and our disk 4 happens to only have one partition on it. And this is our SD card, which is it's an 8 gigabyte SD card that only has one single partition on it that takes up the entire disk basically. You can also do some other commands which will help to see stuff a little clearer. So if you go df and then enter, oh sorry, my face is over some of this. Just run this up here instead. Df. There we go. So up here you can see all the disks listed out, and you can see you've got the availability in 512 byte blocks. That becomes important later. We'll talk about 512 as an important number. We'll talk about it a great many times. You can see used available disks, the percentage of capacity, and you can also see how it's mounted onto the system. So this one down here is the one that we're interested in, which is the dev disk 4 S1. So there's there's two ways you can connect to a disk. Basically, you can read the disk from the individual partition, which is typically how your operating system does it. Your operating system will mount the partition of a disk for you to access. Typically, you're not accessing the whole disk. For our code, we are accessing the whole disk, and there's a reason for that, which I'll explain in a minute. But this just shows you what is mounted here. So this is the number of blocks in 512 blocks in 8 gigabytes that are available, and it's called it's mounted as our volumes logger, which is volumes is a standard way that the Mac operating system will mount an external media, and I've named it logger. So if you open the Finder, you can see we have a disk here called logger, and I have these two log files written into it, which are what we are going to be reading from. So that's it. that's our disk. That's what we're messing with. And I think something that's probably not super obvious to most people, certainly wasn't really obvious to me. It makes perfect sense, but all a disk is it's just a pile of bytes. That's all it is. It's just a big expanse of just bytes. And if the disk doesn't have any data on it, they're just empty bytes. If the disk has data on it, there's some bytes populated somewhere on the disk, and what you have to figure out, or what your operating system has to figure out, is, well, what's on this disk? So like I alluded to earlier, you can just write whatever binary data you want onto a disk, and it's just arbitrary. You can just put whatever you want onto the disk, and as long as you have some software that can read from that disk, which you can effectively think of the whole disk as just a big binary file. If you could just read from that, that's it. As long as you know what to do with those bytes, that's perfectly fine. The reason why we use what we would call like a disk format or a file format is so that when you read that binary data, there's a shared language that can be implemented across different operating systems and different computers that will know how to take the data out of it. So if I plug an SD card into one computer, it understands this is a FAT32 SD card, it writes to it, and then when I plug that out and plug it into another computer, it knows that it's a FAT32 SD card, and it can access the files in the same way that I wrote them on the other computer. So that's all that a disk format is. It's just a shared common language that allows you to know how to pull the data off a disk and how to put the data onto a disk, and it's portable then so that other people can understand it. That's all it is. But ultimately, it's just one big blob of bytes, and that's it. Yeah, I hadn't really ever thought about that before. But as I started working through this project, that started to make more and more sense to me, right? That's all that this format really is. And this is the same as if you have a file format, like, whatever, .jpeg, whatever. All that tells your computer is like, this is how you decode what is in this binary data I've written to this file. This is how you decode what it is. Of course, for the specific example we're talking about, we're treating the entire drive as like a file, basically. We're doing stuff with that file. We're going to extract that data. But at the end, then, when you extract the data, that data has its own format as well, which is the interesting part that you have to then decode. So that's the example of your JPEG or whatever. So anyway, let's get into a little bit more about how my code works. I'll talk about the code. I'll run the code. I'll talk through some numbers and stuff you're going to see on the screen. And then I'll show you some other stuff about how the drive works. So first thing, actually, really good resource for all of this. There's my code that's on GitHub. You find that on my GitHub, carry3 / FAT32Pi. There's a link in the description anyway. But this has been my primary resource for going through all this and understanding what's going on. This and ChatGPT have helped me an incredible amount with figuring out some of this stuff. This article is really, really good. I'll link this in the description too. Just goes through all the details of like the entirety of how the FAT32 file system works. So there's a lot of different parts to this. Basically, your drive, your FAT32 file system is set up with a whole bunch of stuff. These reserved sectors which do specific things. The boot sector, very important. That's one that we'll touch on later. Don't need to worry about most of the rest of this. You can read this if you want to understand what all these are. But the main parts, you have the reserved sector, which is sort of static information, tells you how the drive is set up. Then you've got the FAT region, and then you've got the data region. You can ignore this root directory thing. It only applies to FAT12 and FAT16 file systems. As of FAT32, this isn't relevant anymore. But the two kind of main important parts about how the FAT file system works are the FAT region and the data region. So there's a bunch of numbers I'm going to start throwing around, which you'll see when I show you some of the code running here in a second. But the basic idea of how the FAT file system works. FAT is the file allocation table. The basic idea is we have the data region. So this is where all of the data is actually stored. The data region is just a list, just all bytes. But if you look them in like chunks, they have an idea of a cluster. A cluster is made up of a bunch of sectors. Sectors are each 512 bytes. So within the data region, there's these individual clusters, which are just chunks of bytes of data. And they're supposed to be pretty much the smallest unit of a file that you can store. So if you want to, you have to allocate memory to a file, and the smallest amount of memory you can allocate to a file under the FAT32 is one cluster. So one cluster depends, they can be set up differently, but the basic setup, and the one that I have here, is you've got one cluster is 64 sectors. One sector is 512 bytes. So what you end up with is you end up with 32 kilobytes per cluster. So that means if I have a file and it is exactly 32 kilobytes in size, when I write that file to the disk, it will consume 1 cluster of the disk. And the entirety of the 8 gigabytes that I have on this SD card are made up of 32 kilobyte clusters. So if you do that 8 gigabytes divided by 32 kilobytes, that will give you the total number of clusters available on the disk. And that then, so that's how the files will be broken up and distributed on the disk. But how would you actually know what clusters represent what files? It can't be contiguous, which is basically like, so, you know, if you were to know, oh, the file starts here, I'll read one cluster, then I'll read the next cluster, then I'll read the next cluster, and then read the next cluster. There's no guarantee that adjacent clusters actually combine together to make one file. They can be spread out across the disk in multiple different ways. You may have heard the term disk fragmentation or running a disk defragment. And the idea of that is that, well, your sort of files can be interleaved in different clusters that are non-adjacent. And what that actually leads to is it leads to the file system having to jump around loads to piece together the overall file that's trying to read. So that's not great. You'd obviously just want it to just read sequential chunks out of the file system, but it can't always do that. So let's go back then to the point of, well, okay, if they're not adjacent, then how does it know what clusters to read and where they are? The way it knows that is because of the file allocation table. So the file allocation table is basically just a bunch of pointers. It's implemented what they call as a singly linked list, which is that you start at some root node on it, and then it has a value. The value that it has points to the next node. And that can be anywhere in the table. You don't know where it's going to be. But it has an address, and then you go to that next address, and then all it tells you is, here's the next one you go to, and you go to that address, and so on and so forth, until you get to a special ending address, which is an end of chain marker, it's called. So when you hit that, you know there's no more clusters for this file, so that's it. I've read the end of the file. Now, how does that link to the actual data region? And the way it does it is the number of entries in the FAT table is the same as the number of clusters in the data region. So that might seem unintuitive, but our data region is, you can think of them as just like integer number of clusters. So there's 1 to n clusters. Each cluster is 32 kilobytes. They have an address, basically. So they go 1, 2, 3, 4, 5, blah, blah, blah. The file region, or the FAT region, has 1 entry per each of those. So however n number of clusters there are n number of entries in the FAT table. The entries are tiny. They're very small. They're only 4 bytes each. So the FAT table is much, much, much smaller than the data region itself, but it contains 1 pointer that corresponds to each cluster. This might not be super clear. I can't really explain it much more clearly than that, I don't think. Convince yourself of it. Go and read the documentation, look at the code, run the code, play around with it, and it'll become clear how that mapping works. But it's basically a one-to-one, like, integer ID mapping that's based off of this chain thing, and then that goes to the cluster, and then you read the cluster. Anyway, you have to kind of trust me on that one. So with that said, let's run my code, and I can talk through some other numbers and stuff that you'll see. And yeah, I'll explain things a little bit more maybe. So let's go and have a look. So yeah, this is my code. Have a look at the first bit of the code. So all this does at the start, it imports some stuff. It imports this disk object from this FAT32 module, which is in here. So this is all of the code that's actually doing the work. There's quite a lot. It's like, this is more than 300 lines. All this does is just reads files data. I was hoping it'd be a lot less than this. This also code is definitely not well optimized. It's just kind of hacked together. But in any case, this module contains all the logic for how it works. And then in this main function, I'm just using that to do some demo stuff here. So we start off, first thing we do, we open our file, this is just a standard how you would read a file in Python. Just use the open command. I've pointed it at the file pointer from down here, which I have as disk dev/disk4. So it's going to read the root of that file, which we know just points to our SD card. And I'm reading it as just a binary file. So ORB is opening it as a read-only binary file. And that's that. This will just read bytes. Just read the raw bytes out of the disk, and that's all this will do. So I do this, I open it up here. Then the next thing I do is I define this function here. So this is a weirdness about the specific implementation of what I'm doing here, but basically the SDIO library or code that runs from in my HAL on my chip, what that does is, or all it can do is, it can read 512 bytes at a time, which is a block or a sector, and you give it a what's called a logical block address, and all it does is just reads those 512 bytes. So logical block addresses are just integers, which are chunks. So you start at 1, 512, that's the first 512 bytes of the disk. Then if you pass it 2, it goes 1 over and reads the next 512 bytes, 3 reads the next 512 bytes, so on and so forth. So that's not a super optimal way to access a file system, but because of the constraints of how a very low level system like the STM32 will run with memory and IO constraints, that's all it's capable of doing. And that's also programmatically, that's all that's been exposed to me is a read and a write method that both can just read and write 512 blocks at a time. So I have to implement all of my logic to support just reading and writing 512 blocks at a time. Obviously, this the standard Python open file reading command, and same in Rust as well, can do much more than that. But in a memory constrained environment, all I'll have access to is the ability to do 512 bytes at a time. So that's why I've had to implement this little function, which you then pass into the disk management object, and that's what does the actual reading. So the logic that's implemented in here doesn't actually care about how exactly you're going to read and write those bytes. All it knows is that I have this thing that does 512 blocks at a time, and that's all. So makes it a bit more agnostic, and that will become important for the implementation in Rust, where I'm going to write all the logic, and then I'm just going to pass in the SDIO card reader function, which does exactly this, reads and writes 512 bytes at a time. So very specific implementation detail here that I've had to call out separately, and I did this now just so that I could architect the code to work the way I'm going to need it to work in the future. So that's that. So then I create an instance of my abstraction, I do some initialization, and then I'm going to do a couple of things. So the disk initialization goes off and does a couple of things up front. I haven't talked about this yet, but all your drives, basically FAT32 drives, are going to work off of a set of partitions, which is the stuff that I mentioned down here. You have these like sectors here, which are basically the partitions. It's not super relevant to this problem because my disk, I have set it up just with one single partition, but you could set it up with multiple partitions if you wanted to. The next most important bit is this BIOS parameter block, which I'll talk about that in a second because that's quite important. That is from basically from the setup in here. So within the boot sector, you'll see there's a bit here called the BIOS parameter block. That's very important. Again, you can see this is one of my previously visited articles, which I've been using to understand what's going on with this. But yeah, I'll talk about the BIOS parameter block in a second. So we read these out from the disk. So these are segments of the disk. So we read these out, which then this gives us all the information we need to know to be able to parse the FAT table and the data layer and actually extract the data from the disk. So we do disk init, that populates that data for us. And then I have a couple of things down here. So two methods. One here is I just want to list all the root files. So that's another thing I should mention. My code does technically support reading directories and subdirectories and stuff like that. I've decided for the purposes of what I want to do with this, I'm only ever going to read and write to the root directory, and they're just going to be files, and that's all I care about. So that's all I'm going to implement. I'm not going to implement like nested file structure stuff and all that kind of thing. It's not terribly hard to do. It's just an extra complexity, which I've decided I don't care about. All I'm ever going to do is just write to the root file system. Great. That's fine. So yeah, I list out the root files. I have some object here that's returned that represents the file. I've decided to check some details about the files that are returned. Then if they meet some criteria, I'm going to read the files, and then I'm going to print them to the screen as ASCII. So this is an important part I mentioned before. It's like, well, so I can parse all this raw binary data about what a file is, but then I don't actually know what those files are. They could be JPEGs. They could be anything. So the binary data within them, I don't know what that actually means. So in my case, there's a bunch of text files in here. So I'm just going to read them as ASCII, which is all this method does. It just reads the content as ASCII, and then it'll just print it out to the screen. And that's it. You might be wondering why I'm doing this stuff. There's actually, if you open just like a hex editor and just look at the contents of this disk, there's a ton of files on it, which is weird. You don't expect that, because when you look at it through your finder in your operating system, I can see there's just 2 files here. That's it. They're just 2 log files. So what are all these other folders? There's a whole bunch of different stuff in there. Basically, the FAT32 file system is pretty old, so there's stuff that's in there that's kind of hacks to support different things. File names in particular, there's a specific hack to support long file names that weren't natively supported by DOS, which is the disk operating system, which is basically the root of Windows from back in the day. And yeah, there's other stuff. There's like system folders and other things in there. And all this does is basically just ignores some of that stuff. So that all I'm looking for is actual files. But you'll see there's still some weird little quirk. Even after doing a bunch of filtering and stuff, there's just one thing that I haven't been able to get around. And I'll show you when I run the code what I mean. Okay, let's run the code and see what we get out of it. So to run this, you use uv run main.py, hit enter. Now that's accessing the disk, doing all its bits, and okay, so it spat out some data for us. So if I scroll up, let's start at the top. So the first thing it does, lists out the disk partitions, which it does by just calling disk partitions in here after init. So this is just stored in memory, and we get an array of a bunch of partitions. So for FAT32, there's by default 4 native primary partitions on the disk. You can see here we've got 1 which is populated, and then these other ones here aren't populated at all. So this data comes from something called the master boot record, and this is technically outside of the FAT32 file system. What this actually is this is the first 512 bytes of the disk itself, and all it shows you is just what's on the disk in terms of what partitions are there. There are other things, so the word boot is in there. So if this is a bootable disk, in the master boot record, there will be some stuff in there which is basically very low level boot code that will tell it what to do. This isn't a bootable disk, so it doesn't have that. But all we're specifically interested in, because we know this is just a data disk, is just the partition here. So there's a couple of things that are interesting to note here. The number of sectors. So this is what is this? That's 1, 2. So yeah, it's 15,500,593,472 sectors on the disk. So if you multiply that by 512, that will tell you how many bytes are in this partition, and that should add up to roughly 8 gigabytes, which is the availability on my SD card, 8 gigabyte SD card. meta comment, while I've been messing with this stuff, I've been trying to like, parse the whole disk and stuff, which when it's 8 GB is actually quite difficult to figure out where everything is on the disk. So I was trying to dig out trying to find like an old SD card, if I had one, like a 512 megabyte SD card or something like that. Turns out I can't find one. So, and I also went to try and buy, see if I could buy like a 256 megabyte SD card, and I just can't buy one. I found a 256 gigabyte SD card, which is, it's just weird. You can't buy the tiny ones anymore, which means that manually parsing this data is actually quite difficult. But anyway, so this is telling me that I've got that's how many sectors I have on the disk, how much data is basically there in this partition. And then this is the only other thing that's important immediately, which is the start LBA. So LBA is the logical block address. And this basically says this partition, the data, the what's interesting inside this starts after you've read 100, or after you've traversed 8,192 sectors, which is 8,192 times 512. So that's basically like an offset from the start of the disk. So if you're reading this disk and you want to see, well, where does that FAT32 file system start? The FAT32 file system for this partition starts after that offset. So you'll see in the code, when I flash that up on the screen in a minute, that basically everything we do starts with this partition offset. And that tells us where from the start of the disk we have to start from when we're want to read from this FAT32 partition. So that's all that does. So by reading this, that tells us exactly where we are on the disk and where to start from. So we have to read this because everything that we're going to do after this corresponds to this information. So that's why that's one of the first things we read, is we read the master boot record, figure out the partitions, and by default I've just decided that I'm going to assume my disk is only going to have one partition, and even if it didn't, I'm going to always just pull the first non-empty partition, basically, which is going to be from here. Other things here, which I'm not going to talk about them in any great detail. There's these two values here, the start CHS and the end CHS. So CHS, I think it stands for cylinder head sector. And this is actually an implementation detail from old spinning disk platinum hard drives. And yeah, it's not relevant anymore. It's basically been replaced with the LBA. And this is, basically an old school thing to do with spinning hard drives. And you don't need to worry about that anymore. You can just use the LBA these days. Obviously, our SD card is a full embedded system. There is no spinning drive anyway, so this is not relevant. I'm not even sure, actually, if you are actually using this with a spinning drive these days. I still don't think these are relevant. I think you can just use the LBA. Not sure on that, but anyway, that's an old technological thing to do with spinning disk hard drives. So okay, what have we done? We understand where our drive starts, where our partition starts for our FAT32. So now we have to actually start reading data from the FAT32 file system itself. So the first thing we need to read is the BIOS parameter block, which again I talked about in here. So within our actual FAT32 file system, it's one of the first regions, which is in the reserved sector, is this boot sector, which contains the BIOS parameter block. There's other stuff in here, the FS information sector. This has stuff in it to do with what files are on the disk and what memory is allocated and stuff like that. I haven't done much parsing of this. Basically, from my reading, I have determined that it's actually not super relevant. Some operating systems update this information, some don't. So it can actually go out of sync with the actual data that's on the disk. So the best way to actually know what's on the disk is to read from the disk itself. as opposed to relying on this file system information sector. Also, most implementations of this only read to this when you hit that safely eject button from the drive. So if you ever just yank out SD cards or USB sticks, there's a chance that your file system, the FS information sector, isn't being written to, which means that the information is going to be out of date. So yeah, it shouldn't be relied on. So I've decided for my implementation of this, I'm just going to ignore it. So yeah, all we're interested from this is the BIOS parameter block. So our code sets that up. It reads the BIOS parameter block in the init function, and it's going to print it out here onto the screen, which it has done here. So this is a whole bunch of information. So first thing, bytes per sector, 512, which was the exact same as what we set up here for our partition. We read the first 512 bytes here. That's kind of a standard. So earlier on when I said, the start LBA is 8,192 and then times 512 will give you the offset. That's just sort of standard, but it might not actually be exactly how it is. It is in this case, but it could technically be different. I don't think it is. I think in practice it's always going to be 512, but once you get into your actual FAT32 file system, this bytes per sector doesn't have to be 512. It could be something different. So that's why it's written into the BIOS parameter block exactly how big the sectors on the disk are. So it's 512, which is standard. Same with the number of sectors per cluster, in this case being 64. That could be not 64, could be something else. Reserved sector count 32. So that's the reserved sector count is just this whole thing here. So reserved sectors, so it just tells you how big this section is that has all this information in it. Again, we don't really need to pay attention to that. Number of FATs. So this one is number of file allocation tables that are stored on the disk. You'll notice down here in the FAT region, there's FAT table 1 and FAT table 2, which FAT table 2 is optional. So basically, you can have a duplicate of the file allocation table, and the idea of that is in case it gets corrupted or anything, so it keeps 2 copies to try and keep in sync. I'm ignoring that. So for my implementation, I'm just going to be reading and writing to the first file allocation table. I'm going to ignore the second one. But and a real implementation of this, your operating system would maintain both of those tables. You then have the total sectors. So the information is stored in the BIOS parameter block based on whether it's FAT16 or a FAT32. This is a FAT32 drive. Its format is FAT32. So the information is still there in the BIOS parameter block, but it's just not going to have anything in it. So there's no FAT16 sectors. We've got this same number that we saw before, which we have up here. And that tells us how many sectors we have on the disk. The FAT size, which is written out here. So this is basically how long the FAT is. And that is 1,904 sectors times 512 will give you the amount of bytes. The root cluster starts at 2. That's important. That's basically where the root file system is. And this is defined here. In FAT16 and FAT12, the root file system was a special thing, which you've actually seen here, which is in our data here. This tells us where the root directory starts. In FAT32, it isn't. It's just a data cluster. It's just in the data section, and it's just a cluster, which is a special file directory type, and it has all of the files that are in the root written to it. Again, don't go into that in too much detail, but it's just something to know about. And the BIOS parameter block tells us that. So if you want to know, well, how do I start reading from the disk? You read from here, and it's telling you where that cluster is to start reading from. And yeah, I think, I can just kind of ignore most of the rest of this. It's not super needed. And also some of this is just for convenient naming conventions, just some of the same information renamed, like root cluster is the same there. Classic example of some AI generated code here, that the AI generated some of these things and decided it wanted to rename them for some bizarre reason. And I haven't cleaned that up yet, so that is why that is there. Same with fat size here, as opposed to FAT32 size. It just assumed it's just making this up. Anyway, doesn't matter. Okay, so what does the rest of the code do then? So the rest of my sample code lists the root files. So it goes in, finds that chunk 2, that cluster 2, starts there and iterates through the FAT table from that cluster and finds all the files that are in it. Then my code then takes those files, which are referenced here, and then it reads those files in chunks. So this is a specific implementation as well to do with memory consumption. So I could just try and read the whole file into memory, which I know my computer would be perfectly capable of doing that if they're reasonably sized files. But I don't want to do that because when this runs on an embedded system, I only have 128 kilobytes of RAM available to me. So I can't just read arbitrarily large size files into memory because I'll just run out of memory. So I'm reading in chunks, which these chunks are 32 kilobyte chunks, which have been read in even smaller chunks of 512 bytes at a time. Implementation detail again to do with this. And so yeah, all this does is it'll just iterate through all of my root files and then print them out onto the screen. So starts, first file it happens to have read is this log file 2, which is there, log file 2. And this just contains some lorem ipsum text, and it's just printed that out to the screen, and that's it. I also have log file 1 here, read log file 1. Log file 1 contains a single line that says log line 1. That's it. And now this is the other part that I talked about earlier on, where this is the part that I haven't been able to filter these files out. And when you think about it, I shouldn't be able to either. This is correct. My file system code is doing the right thing. So I have 2 files here, which it's rightly picked up those 2 files and printed them out. But then I have these 2 other files. This one, which is called underscore log dash tilde 2, and another one called underscore log dash tilde 15. Okay. Whatever. I don't know what these are. But when you actually read the file content and print it out in ASCII, most of this is cut off, but you'll see Mac OS X. Interesting. And then down here, com, Apple, Providence, this resource fork intentionally left blank. So that's a thing. It's some internal Apple thing that's doing a thing, and I don't know why. I don't know why it's writing these files. I don't know what Mac OS is doing with these files, but it's some hidden file that Mac OS is doing for some reason. But it's not even a hidden file, because I have my Finder set up to show me hidden files, like, dot hidden files, and it's not even one of those. So as far as the file system, if the FAT32 file system is concerned, these are plain old regular files. They're not system files, they're not hidden files, they're just regular old files. But the Mac OS and the Finder are doing something with them to filter them out. So it's reading that file. Mac OS is reading that file and is saying, oh yeah, that's a special file I do stuff with. Don't need to worry about it. But I don't know what it does or why. But that's just a thing that exists. So this is yet another one of those examples where all I'm doing is reading bytes. So I've opened my drive as a just reading binary data, and all I'm doing is reading the bytes, and the bytes are showing me this and this information. It's up to the software that's consuming that to do something with it. That's it. So, all right, we've covered a lot of ground. I just looked down at my recording time and realized this is 45 minutes so far, basically, of ranting and raving about this stuff. I was going to show you guys the code in here and talk through a little bit, but I think we'd be here for well over an hour if I did that. So I'm not going to talk through this in any great detail. Also, code is garbage. Just throw that out there straight away. Chunks of this are just AI generated, because ChatGPT is helping me with this. And yeah, so it's not particularly good code, but it does work. That's kind of, some of it's kind of dense as well, so it's a little bit hard to talk through. But link is in the description, so you can feel free to go through this code and, you know, convince yourself of it. So yeah, that's that. I gotta leave it there for in terms of going through the code. Yeah, let's leave that there. So yeah, you can go through this code, convince yourself how it works, and maybe I'll do another video where I talk about it in a bit more detail. I think the next step for me is I need to figure out how to write data. So right now, all I can do is read the data. Can't write it yet. It's kind of breaking my brain, the write, a little bit. I know conceptually what I have to do for it. It's just a little bit complicated, and there's a lot of there's some kind of edge cases and stuff to it. So I'm going to mess around with that a bit more. I was doing some messing with it, and I just cleared it all out because I wasn't happy with what I had written. So I'm going to start again on some of that write code, and hopefully get that written in the next week or so. And then what I will do is maybe then I might go through all of the code in a bit more detail, the reading and the writing, and then show you guys a bit more of a demo of it. Then the next step is to turn all of that into Rust code and then implement it on my little STM32 board, and then finally be able to log files to the SD card, which, I mean, I thought this would be like a week, and at this rate, it looks like it's going to be several months of trying to just do that. But, you know, for me, I don't mind that. I don't really care how long these projects take me to do. I just something to keep myself entertained with and distracted, and also something that I'm learning. So I totally don't mind the grind of working through this, because I'm also learning a ton by doing it. So having a lot of fun there. So yeah, that's it. I'm going to leave it here for this video. If you manage to get through all of this, fair play. You're doing the Lord's work. But yeah, thanks very much for watching. I hope you learned something. Hope you got something from it. Check out the links in the description for all the resources and the code, etc. And yeah, we're going to leave it there. I will see you guys in the next one. Bye bye.